Hello, everyone. My name is Zhang. I'm currently a postdoc researcher at the University of Illinois, Urbana-Champaign. So it is my great honor here today to present our recent work on developing a crowd-guided neural architecture searching approach to address this disaster damage assessment problem. So we first introduce some background of the applications that we worked in this paper. So we observed that in the disaster-related events, severe damages could simultaneously happen in many places. However, given the limited emergency response resources, one key question is how to prioritize the response team's operation to save people's lives. So here, we focus on an important application in disaster response, named disaster damage assessment, that aims to automatically assess the damage severity of the affected areas in a disaster event by leveraging this social media image data for the timely and effective disaster response. So here, we actually observe that the performance of current deep learning-based DDA solution is very sensitive to the neural architecture selection in their design. More specifically, we observe that even a slightly difference in the neural architecture could have a significant impact on the performance of the corresponding DDA solutions. So in this example, we compare the DDA performance of similar neural architectures. We observe that even only one layer difference in the neural architectures could lead to the incorrect disaster damage assessment results. So motivated by such observation, we study an optimal neural architecture search problem in DDA applications, where our goal is to identify the neural architecture that achieves the optimal damage assessment performance without the input from the AI experts. In particular, we observe that the human perceptions is often more reliable and consistent than the AI algorithms in terms of identifying the disaster damage severity of affected areas from the image. And such human intelligence could greatly help us to infer the probability that a given neural architectures make the correct DDA estimation and discover the optimal one that generates the best DDA results. So in this paper, we actually developed a crowd-guided neural architecture search framework by utilizing the human intelligence from the crowdsourcing system to identify the optimal neural architecture for a DDA application. So in particular, our design consists of two key modules. So first, we have the CSSD module, which designs a set of sequential neural network search subspace, which is on the top of a pre-trained damage assessment network. The goal is to effectively reduce the search space for our crowd-guided neural architecture searching problem. And then we have the COAS module that develops a principled crowd AI integration model to incorporate the imperfect crowd response to guide the selection of the optimal neural architecture from the search space identified by the CSSD module. So next, we go into the detail of our design. So first, the objective of our first module is to identify a reduced search space, which is in the order of magnitude smaller than a regular neural architecture search space, and also has a high likelihood to include the optimal neural architecture. And we refer to such a reduced search space as the crowd manageable search space, where the crowd worker can identify the optimal neural architectures from the crowd manageable search space accordingly. Our design first contains a feature extraction search space to discover the optimal pre-trained CNN layers required to extract the deep visual features from the images. And then the convolutional operation search space is used to identify the optimal number of convolutional layers to further process the extracted deep visual features. And finally, we have the dense layer search space, which is used to discover the optimal number of required dense layers to estimate the damage severity level of the input image using the processed deep visual features. In addition, our designs also include this skip connection operation that allows our solution to skip the convolutional operation if our system decided that the convolution operation is not a part of the optimal neural architecture. And then in our next module, we first introduced a crowdsourcing portal on the Amazon Mechanic Turk to collect the human intelligence. So our COAS module then designs a crowd AI integration model that is used to accurately identify the optimal neural architectures. We observed that every neural architectures and every participating crowd workers, they all generate their own estimations on the damage severity levels. Therefore, we can treat both the neural architectures and the crowd workers as the data sources with unknown reliabilities that makes their estimations of these unknown damage severity labels. The goal here is to use it to estimate the reliabilities of each neural architectures and identify the optimal ones through the expectation maximization. In our evaluation, we use the two real-world datasets on the disaster damage assessment. The datasets consist of the social media images collected from the two different disaster events, the Typhoon Hakupit in Philippines and the California wildfires here in the United States. So the two datasets have the very different damage characteristics, including the damage types, the objective layouts, and the color distribution, which actually create a very challenging evaluation scenarios for our CrowdNAS framework. So finally, we show an example of our evaluation results, where we actually vary the ratio of the studied images that are sent to the crowdsourcing system to collect the crowd labels. For example, the 10% here means that we send the 10% of the studied images for the crowd labeling. And we also compare our CrowdNAS with a rich set of AI, crowd AI, and the neural architecture searching baselines. For example, this proxy-less baseline is the lightweight neural architecture searching framework that conducts the network searching on the cell-based architecture building blocks to ensure this desirable neural architecture searching process. Here, we observe that our schemes consistently outperform all compared baselines on all evaluation metrics by achieving the best data classification accuracy. So in particular, the performance gain of our CrowdNAS over the compared baselines mainly comes from the fact that we actually developed a crowd-guided neural architecture searching system, which effectively identify the optimal neural network architectures in the design space to reduce the bias and errors compared to the baselines designed by the AI experts by leveraging this imperfect crowd input. That concludes my presentation. Please feel free to let me know if you have any questions. Thank you.